friends, today we shall be discussing some of the fundamental principles of physics that we use for deriving the relationship useful for our hydraulic engineering. In fact, these fundamental principles are same, almost same, but of course, some specialties are there definitely. And then same means I am meaning that it is, suppose when it is not a fluid, in some other solid also we can apply this sort of principle, but there will be some speciality definitely. And so today's discussion is basically on conservation principles and governing equation. Basically these conservation principles lead to some governing equations of flow. Well, what are the fundamental physical principles? Well, some governing equation will definitely be coming, but before that, understanding these physical principles are very, very important. And then after understanding these physical principles, when we try to derive some mathematical relation from these physical principles, then what are the assumptions we are making? This is also these are also very, very important, and that way we will try to highlight some of those issues also in this particular lecture. Well, and as we all know that what are the fundamental principle of physics, that is the conservation of mass. You can concentrate to the slide, that is conservation of mass, and we know that in fluid, particularly in say water, when we talk about water, then this we can lead us to continuity equation. How? Say conservation of mass means mass is conserved, that is, say mass means if a volume of flow is say V, and then it is that we can find that in a flowing fluid, suppose it is flowing with a area A, say this cross sectional area is A. Let me draw a three-dimensional view. Suppose this cross sectional area is A, and then it is flowing with a velocity V, and then A into V, we can say A into V is equal to Q, area into velocity is equal to Q, that is all right. And then this Q multiplied by rho, rho Q gives us basically the mass flowing, say mass flowing per unit time through this section. And then when we say that conservation of mass, we talk that this mass flowing through this section and at a downstream, say mass flowing through this section will be same. What mass we are having here, what mass we are getting here will be same, unless there is a lateral flow from this side or lateral flow from that side. Well, and that is what the conservation principle. So rho Q is rho Q at section 1, suppose this is section 2, then we can call in simple, that is rho Q at section 1 is equal to rho Q at section 2. Now, in fluid, suppose if it is a compressible fluid, then it will be rho 1 and rho 2 will be different, rho 1 and rho 2 can be different, but in water this rho 1 and rho 2 will be same. So what we can have, that is the Q is equal to ultimately Q1 is equal to Q2, and which we call as a continuity condition. So this lead to continuity equation. Of course, this is just in a very simple term I am trying to explain. And then when we talk about say conservation of momentum, so we know that mass into velocity gives us the momentum. Well, by conservation of momentum, what we mean, that suppose momentum in a upstream section, we are calculating momentum in a upstream section, and then momentum at a downstream section, then whether these two momentum will be equal, or by conservation of momentum, what we mean basically. As we know that from the Newton's law, that is the change of momentum, rate of change of momentum is equal to the applied force. So, momentum at upstream and momentum at downstream, these two sections upstream and downstream, momentum between these two sections may be different, but the change of this momentum per unit time, rate of change of momentum per unit time will be equal to the external force. So, that is what we mean by conservation of momentum. Similarly, when we talk about, say, that is why this formula we use, that F is equal to mass into acceleration. This is a well known relation. Basically, what we are meaning by this formula, that is the force, as we are saying, force is equal to rate of change of momentum, say rate of change of momentum, okay. So, change of momentum per unit time, say in unit time, if we have some mass into velocity here and v1 at a particular section, and then we have, say, mass into velocity at another section, then if we talk about per unit time, then we can divide it by time, and then say when mass is constant for a particular fluid we are talking about, say for this thing, then what we can write, this is equal to v1 minus v2 by t, and this is nothing but change in velocity per unit time. So, we can write this as mass into acceleration. So, that way we can ultimately come to this relation, that is the force is equal to ma, that is well known Newton's second law of motion. Then the third basic principle is conservation of energy. Well, now conservation of energy, again here also, suppose if we consider energy at upstream section and energy at a downstream section, well, where the energy will be more? Definitely when a flow is moving from upstream to downstream, when a flow is moving from upstream to downstream, then energy level at upstream must be more than energy level at downstream, then only that is why the flow is moving from this direction. Okay. Now, so by energy conservation, what we mean, that whatever energy we are having here, whatever energy we are having here, it is not that this should be identical, but some energy can be lost here. So, energy at this point plus loss of energy during this flow, if we add, then we get, suppose if we deduct the loss of energy from this one, then we are getting the energy at this point. So, energy is getting conserved. I mean, it can be transferred to some other form, or it can be used. Suppose somewhere a lot of turbulence is getting created, some energy is getting lost there. So, energy at upstream and energy at downstream will be definitely different, but some energy is being used in the creation of this turbulence and all. So, that way we have basically three principles, and from this three principle we can have three equation, and these three conservation laws, as you can refer to the slide, that these three conservation laws describe the interaction between a system and the surrounding. So, when we talk about a fluid, when we talk about a flow, then we, for deriving the equation, we will define a system. We will define a system. By a system, what I mean, that we will define a boundary, and within that boundary the interaction, or we will observe the things within that boundary, but always the things what is going on within the boundary will be having some relationship with the things existing outside the boundary, and that is we call that environment, system environment. So, there will be some interaction between system environment and the system, and these three principles we use for explaining that, and then we get some equation. Out of that we derive some equation. Well, now with these equations we can do lot. Once we get the equation, then mathematically we are getting the equation, then we can just solve some of the problem associated with the flow. Well, but one interesting point is that many author uses these equations, that means say three equation we are having, many author uses this equation, and you will be finding that, rather we find that sometimes the equation, suppose continuity equation is looking different, and then another author is using his continuity equation is looking different, momentum equation is looking different. So when we talk about we talk from different point of view, then we derive the equation from different point of view, our equation take different shapes, and then many a time we get confused that okay, which is actually correct form or which form we should use for what purpose. And in those aspects we should know that when we are getting a different form means we are using a different model of the flow. We are using a different model of the flow, and that way we are getting different forms of the equation, and then we are making different assumption in deriving that equations, and that's why we are getting different form of the equation. Basically the physical principles are same: conservation of mass, conservation of momentum, and conservation of equation energy, but equations form may be different because of considering different assumption there. Well, and another point I want to just say here that see in flow, when in open channel flow, when we do study, then for any section we are interested to know what is the flow velocity, what is the depth of flow, and then say what is the discharge. Now already we have seen that if we know the depth of flow and if we know the sectional area, that means sectional shape, if we know the sectional shape, then knowing the depth we will be able to know what the sectional area is. And if we know the velocity, then say the product of this velocity and the sectional area will be getting the discharge. So our interest is generally to know the flow velocity, the depth of flow, and the discharge. But out of these things, basically if we can get two, then we can get the third one. If we suppose know q, then if we know the velocity, we can calculate the y, that is the depth, or if we know the depth, if we know the velocity, we can calculate q. So like that. So two unknown generally remain in our analysis. And then from very basics of our mathematics, that if we have two unknown, then to solve for this two unknown we require two equation. Well, then fortunately we have three equation. One is that conservation of mass, from that principle we get continuity equation. Then again from conservation of momentum we get one equation that is called as momentum equation. Then again from conservation of energy we get one equation that is called energy equation. Okay? And basically these momentum and energy equation that we can call as the equation of motion also. Now these two equations are more or less same, but with some differences that we will be coming later. And say out of these three equations, for solving our problem where we have two unknown variable, only we have two unknown variable, for these two unknown variable, for solving that problem we need two equations. So what we can do, we can choose two equations. Say we are choosing mass and equation of mass, conservation of mass, and the equation of conservation of momentum. So continuity equation and say momentum equation. Again sometimes we can select, okay, we can take continuity equation and energy equation. Now which two we will be taking, and that two in fact we call as a say continuity momentum couple or continuity energy couple, like that also we say. Now which two we will be selecting, that depends upon the problem. Say for example we have a situation where flow is moving like this, where let me draw here. Suppose we have a situation here, flow is somehow coming like this, and then this is moving like this, lot of turbulence in this portion, and then it is moving like this. So now we want to relate what is going on here and what is going on here, and then we want to derive some relationship between these two value to this section. Now if we go for energy equation here, what will happen basically in this portion, because of turbulence lot of energy loss is there, and we may not be in a position to have full understanding of how much energy is getting lost. So, if we try to equate the energy at here, this will be wrong. We will have to do energy at here minus energy at here, energy loss is equal to energy here. So, then energy equation application may be difficult, but if we talk about the momentum, then if we consider this as the fluid to tell our consider flow field under consideration, then we see what are the forces acting here, what are the forces acting here, then we can see what are the external forces acting here. Then we know the situation here, we know what is the momentum here, then we know what is the momentum here. So, in that case we can relate the change of momentum or rate of change of momentum to the external force without bringing in the complexity of energy loss in between. In that case probably momentum equation will be better. So, like that, considering or looking into the situation, we need to select our equation. Well, and now let me explain some of the point regarding the model flow. Why we are coming to this point? At very initial stage we may not require these things, but what I feel that if we discuss these points, then we will be knowing why the different equation or why the same equation means equation derived from the same principle takes different shape, and which shape we are using, that should be clear. Okay. So, say before expressing, you can concentrate on the slide, that before expressing any of this physical principle mathematically, we must visualize the flow in a systematic manner. We must visualize the flow in a systematic manner, and that is what actually how we visualize, that is what we call as a model of flow. Okay. Thus, we can have some model of flow, and basic equations are derived by applying these principles. These principles means mass conservation, momentum conservation and energy conservation to a suitable model of flow, Okay. And as I have already said, that depending on the model, what model we are choosing, a model of flow, and depending on the assumption that we are making, the derived equation will be of different form. Okay. Now, say model of flow 1, we can, one very popular term here in hydraulics we use is control volume. Say this is one control volume. Okay. You can just concentrate into the slide. This we are using that this is a control volume. We are naming this as a control volume. Okay. And this surface of that volume we are saying as control surface. Well, now here if we just consider a small area, then there will be suppose this volume is small volume. So, let me write it as say we can write it as dV, small volume, and then what the mass is we can write rho into dV, this one. Okay. Anyway, that will be coming later again, but first let me talk about the flow model. Say in one of the model, what we are interested that we see what is happening inside this control volume, and the flow is say moving like that, flow is passing this way, and what we mean that fluid mass, suppose a fluid element is here, it is flowing through this and it is reaching this point. Our interest is not that what is happening to this fluid mass, say it is carrying something and it is going there, what is happening to this particular fluid mass, we are not interested. Our interest is to see what is going on within this boundary, So, this sort of system we call that control volume fixed in space, Again, in another model, what we can consider that say this is the volume and it is not standing, it is in this space, it is not fixed, it is moving, say it is moving with the flow, it is moving. So, at this moment it is there, and the next moment it can move. And what is that mass within that control volume? This also sometimes referred as control volume, and or we can call this as a mass, and these things itself we can call as a system, and this system is moving, this system is moving. And so, we can call that a system of fixed mass, moving with the fluid, Well, so this is another way of just making the model of the flow before analyzing it. Now, so these two systems when we consider, then our derived equation will be of different type. Suppose we say that this mass is moving, then it can be compressed, it can be expand also, like that. When it is getting compressed or expanded, means its volume can keep on changing, but this mass is not changing, its mass is not changing. So, if we consider a small volume, small elementary volume, and then suppose this small elementary volume is say dV, then the mass of this small elementary volume, V cut I am using, and then it will be, say mass will be, we can write rho into dV, and then say we can write d dt, that is the change of this mass. How much will be the total mass? First we need to say how much is the total mass. That will be, if we integrate it over the volume, that is the volume integral, this will be say rho dV, and then the change of this mass with respect to time is equal to 0. That way also we can have our equation. Okay. This we are writing as say d dt, capital D dt, because we are talking about a substantial derivative here. As the fluid mass is moving, so there can be change due to its movement, as well as there can be change due to time also. So, that way we are using this term that we will be discussing in more detail of course later, but here just to give you introduction I am writing this expression. But now, when we talk about this system, here also we can have a small volume, say this is dV, and then we can d of volume, and then we can have that rho is the density. So, this is the mass. Now, here what will happen, that total change when we talk about, suppose total change of this control volume, then we can say that the change in the the mass of this control volume, if we say, then it will be that the what change here it is occurring. If we talk about decrease or increase, suppose the change in decrease in this entire control volume is equal to what is going out. If I consider a surface, say small surface ds, and say using velocity in vector form, suppose I am writing v, because now we need to consider direction also. From here if I consider it is going out, from here if I consider in the opposite direction, then it is coming in. So, if I just talk about the entire surface, when we integrate it, it will mean that what is coming in and what is going out, everything. So, what is coming in, what is going out, and that will indicate what the change is. So, that we can write as, suppose what is the small volume, that we can write rho into dV, this is indicating rho into dV, this is indicating the small mass, and that if we integrate over the entire volume, entire control volume, then we are getting this volume, and change of this mass we can have say del t, and this plus, suppose over the surface something is going out. So, what is going out through this small surface, that we can have say in unit time how much is going, because we are talking about per unit time. So, what is going on out in unit time is the this surface area into the velocity will be the volume of flow that is going in unit time, and if I multiply it by rho, so V rho into V means vector velocity, and then it is also in vector notation ds we are getting. So, this much is the things that is going out from this part, and if I integrate it over the surface, then I am getting the total mass that is flowing out from this, and that way this total summation, if we say that it is not changing, that this total summation should be equal to 0. So, we are getting two different form. Well, then rather than considering this entire volume, we can again sometime consider as a infinitesimal small volume like that. We can consider small volume like that of definite shape, and here also we can consider that flow is moving through it in this case, and say we are considering another small shape here, and then we are saying that it is moving with the flow, So, it will be having a velocity in this direction. At the next moment it can move in this direction also, but at this point it has a velocity in this direction, and then flow is moving. So, here this element is moving, but the concept is same, but here we are considering say infinitesimal small element. Infinitesimal small element we are considering. Now, when we are considering a definite shape, then we can write say this as dx, then this we can write as say dy, this height, and this we can write as dz. Now, again if we derive our relation based on this understanding, then it will be taking a different shape. For example, just this a small point I want to note here. Suppose the flow velocity, let me just draw it like that. Okay, the flow velocity at this point is suppose u. Then the flow velocity u and rho u, and then how much total volume is moving through this part, that we can write as u, and the sectional area will be dz into dy, and then multiplied by rho we are getting what the flow is here. And then on the other side, what we can do, that here the flow velocity is u, then or say when the flow velocity is u, per unit area the mass flowing is rho u. So, this rho u is definitely here, then plus if there is a rate of change of mass flow, if there is a rate of change of mass flow in this direction with respect to x, that means if we write say del rho u del x, suppose there is a rate of change of mass flow in this direction, then after a distance dx, it will be having a total change of this mass. So, rate of change of mass flow at this phase can be written as this one, and again then if this is the rate of change of mass flow per unit area, then total change will be this multiplied by, again we can put dz into dy, this cross sectional area. So, dz into dy. Well, now that is just I am relating this part and that part. From this side again we can do something and some other equation. I am not going for deriving the entire equation, but what I am meaning here, we are using a term del rho u del x, that is the mass flow, rate of mass flow. We are considering that it is differentiable. Now, when we can consider this as differentiable, when this change is continuous. say the velocity vector is continuous, so value of the velocity is continuous and these are continuous, then only we can use this differential term. Otherwise, it will not be possible. So, the flow of velocity or the depth, these things will have to be considered as continuous in this sort of analysis. But when we are talking about this control volume and we are talking about this integral form, here we are getting it in differential form. Of course, I am not writing the final equation, but this is the differentiation term we are using. Here we are not using those terms in this part, and that is why here that sort of assumption is not required, means in this part. Well, so this equation we will be calling as integral form, and this we can call as say differential form. Of course, I am not writing the, I am repeating, I am not writing the entire equation here, and then here also it is integral form, here also it is differential form. But when we go by this concept, when our flow model is this one, then we call this one, means the first one that I am considering. You can concentrate on the slide. When my flow model is this one, then we call this as the equation that we get from this starting from this point, then we call this as this equation to be in conservation form. We call in conservation form. And this we call, if we go by this concept, then what the ultimate equation we get, that we call as in non-conservation form. Of course, it does not mean that it is not related to conservation of mass or conservation of momentum, but the name we give as non-conservation form. Here it is conservation form. So that way you could see that when our flow model is different, then our equation ultimately that we get is different. Again, flow model means with this again we get different, but one point is that we can always, after deriving an equation, we can go from one form to the other form. From integral form to the differential form we can go, and from again non-conservation form to the conservation form we can go, from conservation form to the non-conservation form we can go, and this way our energy equation or momentum equation or the continuity equation can take different shape. Well, we are not going into much detail of this part, but still I am just considering, I am just trying to explain some of the very fundamental. Well, then you can concentrate again on the slide, the Reynolds transform theorem. This is also one of the important theorem that we need to know before deriving those equations. Well, what it means, that Reynolds transform theorem relates the flow variable of a specified fluid mass. That means, suppose we know the flow variable of a specified fluid mass, then we can relate this property, that is flow variable of a specified fluid mass, to that of a specified fluid region. By fluid region we mean say control volume, and then say if we know the property of the fluid mass, then that we can relate to the property of the entire fluid region. This is what the Reynolds transport state. And of course, in hydraulic engineering we are generally more interested in the flow in a region, Say normally when we say, when we try to understand a flow, we see that what is happening to a particular region. Suppose when we talk about a channel, we will be interested to know that in a channel reach what is happening, how the flow are changing or what is happening. Of course, how a individual fluid particle is moving, or say fluid mass, a small fluid mass is moving from one point to other, and what is happening to that particular fluid mass, that can be of course of our interest, but in hydraulic engineering generally we are more interested in this part, that is in flow in a region rather than flowing motion of a rather than following motion of a particular fluid particle or fluid mass. Well, and Reynolds transport theorem relates the flow variable in a control volume to that of the system. Okay. So, that is what is Reynolds transport theorem, and for just explaining that part we use two terms. We use the term extensive property of a system and intensive property. Okay. Now, what is extensive property and what is intensive property, that we need to discuss before writing some of the equation. Well, what is extensive property and intensive property? Well, suppose B, let me write, suppose B, if say B is the extensive property, well, by property what we are meaning, this can be, suppose we are considering a system, it may be like that, say a channel. Okay, let me talk about a channel, and then say this is the control volume we are talking about, and we are considering this system, suppose the fluid what is flowing here, and we are concerned about this particular things. Okay. Then this B may be this capital B by capital B, we are meaning extensive property, and this extensive property, or by say simply by property what we meaning, say mass can be one property, then say momentum can be one property. So, that way different things, by property we are meaning different things. If B is the extensive property, then say if we use the symbol beta for intensive property, then say intensive property, if we use the symbol beta, then intensive property means that amount of extensive property. So, when we talk about mass, suppose amount of mass, okay, it can be amount of mass also, it can be amount of momentum also. So, it can be amount of any property. So, amount of extensive property per unit mass, that is what the intensive property we call. So, intensive property means amount of extensive property per unit mass, amount of extensive property per unit mass, and generally we talk about a very small mass, and then we see that we try to see that if this mass tends to 0, then what is happening to that. So, beta is basically, beta we can write as, say, what is the small extensive property that has in small amount of mass, and we write that limit delta m tends to 0. So, very small element we talk about, this property we call as a intensive property. Well, now let me again draw this diagram. Say this is a control volume, and we have a small volume dV, V cut I am writing, and then say intensive property of this is suppose beta, intensive property of this is small beta, and this small volume we generally refer as, we call as a differential volume, okay, differential volume. Well, now say this differential volume has some intensive property beta. Now, knowing this intensive property beta, we can find out what will be the extensive property of the entire control volume. What is, I mean, corresponding extensive property. Suppose if we talk about the mass here, then what is the mass of the entire control volume? That we can find out, say B of the control volume is equal to, we can integrate it over the control volume, I am writing the volume, and then it is say beta is the intensive property, that means it is the that particular property per unit mass. So, what will be the mass here? If the volume is dV, we need to multiply it by rho, so that we are getting mass. So, that means in this mass this is the intensive property. So, if you integrate it over the control volume, we are getting the total extensive property of the entire system. So, this is how we relate. And for example, let me give an example. Say, for example, if we talk about say our, let me take our property is, say the property is mass, property is mass. Okay, we can talk about momentum also. This can be mass, momentum, anything. And then if say B is mass of water, if B is mass of water, then corresponding intensive property, will be that means corresponding intensive property means we are talking about again mass only, that we can write that limit delta m tends to 0. Now, we are talking about mass. So, our property itself is say mass, small property, a small mass in that small area, and that way it will be this mass and then per unit mass. So, this is equal to 1. So, what we can write that if our mass is the property, then the beta is, if capital B extensive property is mass, then intensive property become 1. And then if our suppose extensive property, if capital B, that is the extensive property, is momentum, suppose if extensive property is momentum, then our intensive property will be what? Then our intensive property will be intensive property beta, we can write as intensive property beta, we can write as say limit again delta m tends to 0, you can write say momentum of this small mass we can write as dv into delta m, this is the velocity into this, and per unit mass, okay. So, when we write like that, ultimately this become, when delta m tends to 0 or whatever it is, this will get cancelled, ultimately beta is equal to v. That means this is the velocity. So, when our extensive property is momentum, corresponding extensive property is momentum, then corresponding intensive property is the velocity. So, that way we can have this sort of relation between extensive property and intensive property. And then already we have explained what this Reynolds transport theorem state, that it relates the flow variable of a specific fluid mass to that of the specific to that of a specified fluid region. So, from that if we come here, then we can of course write that, suppose let for a particular system we have extensive property of the B system is say B, and then change of that extensive property with respect to time if we write. Now, let me see that what corresponding, suppose this B is the extensive property, corresponding intensive property is say beta, corresponding intensive property is beta, and if we talk about a small elementary volume dV, then per unit mass it will be rho dV. So, per unit mass is B, that property, and so B multiplied by the small mass of that small differential volume dV, then we are getting the intensive property, and that we can integrate over the control volume. And then when we are talking about d dt, that is the total differentiation of the extensive property, then we can call the differentiation of the intensive property, then plus what is that, what is coming into the system and what is going out from the system. If we talk say decrease, then we can say that plus what is, if it is say decreasing that thing, suppose we are talking about momentum or mass, then if it is decreasing, then we can say that what is going out and what is coming in, that also we can write. So, this will be, we can write say beta and then if the sectional area is A, if the sectional area is A, let us consider, we are just writing this for one dimensional system. If the sectional area is A, so this sectional area is A, if this sectional area is A, and then this is suppose B, this sectional area is B, then sorry, it is A1 and this is suppose A2, or let me write it as A itself in the control volume. Then what we can have, this is equal to beta into, if the velocity here is V, then A into V is the volume coming in, and multiplied by rho, it will be the mass coming in. Then intensity property of that mass, if we say that this is going out, and then again we can write this out itself indicating whether it is in the one section or two section, that is say out, then we can have, using the sign itself negative here, we can write beta rho A V in. If we are talking about decrease, then what is coming in we will have to deduct, and then what is going out we are just adding up, and that way we are finding the changes. So, this way we can find out a relationship between the extensive property and the intensive property, and this sort of relation we can use for any of the intensive property, any of the property of fluid, and we can go for deriving some equation. Okay. And from this fundamental relation we start and we go for deriving what is momentum equation or what is energy equation that we can do. Well, these are some of the very fundamentals of the fluid, some of the very fundamentals of the theories that are used for deriving some of our relation. Of course, just to start without going for this sort of without going for application of this sort of theories, for a very simple situation means when we consider our flow to be steady, it is very simple, and then for when we consider this to be one dimensional, then again it is very simple. So, for those simple situation we can derive some of the relation in a very convenient way. So, let us see for a simple situation first how we can derive this continuity equation and momentum equation. Now, please concentrate onto the slide. We want to discuss it briefly. Of course, more details of this continuity equation and momentum equation that we will be discussing when we will be discussing unsteady flow, and right at this moment we will be just introducing some of the simple equation that we use. Well, in the slide you can see that, say, let me consider first we are talking about continuity equation. Okay. Let this be a channel, one dimensional we are talking about, and then flow is moving like this, and let me consider two section, this is 1 and 2, okay, section 1 and section 2, and say let me draw the cross section, not here, let me draw the cross section here. Say this is for the section 1, and on the other side I am drawing the section for the 2, okay, and flow level is this much here corresponding to that, and flow level here is this much corresponding to that. Okay. Now, say just like the case when we did earlier in the last class, let me consider, say this is a small elementary area and the flow velocity through this be small v, and then this area is, sectional area is dA1 and the small velocity is v1. Here also we can consider a small elementary area dA2, and then flow velocity through this is say v2. then about the from using the conservation of mass principle, how much is the volume or how much is the mass flowing through this section per unit time, that we can find out, that is equal to say V1 into dA, that is the volume flowing through it per unit time, and then multiplying by rho 1. Okay, let me write rho 1 density at this particular section, and if we integrate it over the area then we can get that, of course this is, we can integrate it over the depth also, ultimately over the area. So, this is the mass flowing through this section per unit time through this section, and then mass flowing through the section 2, that we can write again the same expression, that rho 2 V2 and dA 2, and then integrate it over the area A2. Well, then as per our conservation principle, this 2 should be equal, provided that there is no lateral inflow or outflow from the, no lateral flow to this system, to the system. Our system is now this one, our system is this one. Now, this is basically the continuity equation in simple term, and suppose if it is water, for water flow is incompressible, so what we can do, flow is incompressible means rho 1 is equal to rho 2, and so this is equal to say rho, so rho is not, we can just cancel this each other, and we can write integration of V1 dA1 is equal to integration of V2 dA2. Now, if we consider that, if we remember our earlier discussion, say, well, I am stating here again, integration of say V1 dA1 equal to integration of V2 dA2. Now, if we just consider that at section 1, suppose it is our mean velocity Vm, then what is that mean velocity expression that we know, that if we integrate the individual velocity at a particular section, and then if we have the total flow discharge through this section divided by the say total sectional area A1, then this is our mean velocity. This is the expression for mean velocity. So, that means what we are getting, that integration of V1 dA1 is nothing but Vm into A, So, we can write that Vm at 1, section 1 into A1 is equal to, similarly here also Vm2 into A2, and Vm1 into A1, Vm2 into A2, these are nothing but we can write Q1 is equal to Q2, and this is what our continuity equation. Well, now when we write this sort of continuity equation, we should remember one point, that our velocity that we are using, that is V1A1, this V is the average velocity or mean velocity. Well, now let me discuss how, in a very simple way, this is for a steady situation we are writing this equation, and that is why use of all those theorem are not coming into this derivation. Well, now let me see what about the momentum equation. Momentum equation again, that is for say steady state, momentum equation for steady state we are talking about. Again, let me consider the same way, say this is the flow occurring, and this is not uniform flow, there can be difference in flow, and this is one section, this is another section. Well, now in momentum equation, our interest is to first know what is the momentum here. Say the flow velocity here is V1. Now, we know that by V1 what we are meaning, that this is the average velocity of this one, and then say flow velocity here is at V2, and suppose the pressure, or we will be interested to know the force. Well, first let us cover what the momentum is. So, the sectional area at this is again this one, and here suppose it is this one, and suppose the Q discharge flowing is Q, discharge flowing is Q here, and discharge flowing through this part is not changing. So, it is also Q. Now, we know what is continuity. So, in this section Q is flowing here, Q is flowing there also, Q is flowing there also. So, what will be the mass? Mass will be equal to rho into Q, density into Q is the mass. Then if we multiply it by the velocity v1, then we are getting the momentum. Of course, this rho we can write in terms of unit weight also as gamma by g. This is also one way we can write, and this is of course the momentum, but with that we need to put the momentum coefficient that we did discuss earlier. Of course, do not confuse this as intensity property or something like that. This is representing beta is the momentum coefficient. So, this is the momentum at that point, and then momentum at this point will be, so it will be beta 2 into, so momentum coefficient can be different here, gamma by g and q into v2. Now, this momentum we are always talking about per unit time, because the mass what we are taking is the volume flowing in unit time, volume flowing in unit time. So, rate of change of momentum means already we are talking about the momentum flowing per unit time here. So, rate of change of momentum we can write rate of change of momentum, that we can write as say gamma by g into beta 2 q v2, what the momentum we are getting here, minus this gamma by g we are keeping common, minus beta 1 q v1. Okay. Now, q being common, we can write it as gamma q by g and say beta 2 v2 minus beta 1 v1. Now, let us see what are the forces. This is the change of momentum per unit time, and then what are the forces that is acting on this particular section. Okay. The force is basically, if its weight is W, then one force acting in this direction, that is equal to, if this angle is theta, then it is equal to W sin theta, that force is there. This is acting in this direction, and then if the depth up to the centroid is z bar, then pressure, if we write, then what is the pressure, average pressure we can get at this point, say it is gamma into z bar, gamma into z bar is the average pressure multiplied by the area. So, what we can write, this pressure force will be gamma into z bar, z1 bar, let me write. Here it will be, suppose depth up to the centroid may be z2 bar. So, pressure will be gamma into z2 bar, and that is the average pressure. So, we are multiplying by the entire sectional area to get the force. So, pressure is equal to gamma z1 bar and multiplied by the area, So, we will be getting the force. This is the force which is acting from this direction. So, this force is gamma z bar into A1, gamma z1 bar A1, and then force acting from the other side, because our control volume is this one, and force acting from the other side, this will be just opposite to this force. So, we can write minus gamma z2 bar A2, this is z1 bar A1 and this is z2 bar A2. Then what are the other forces? What are the other forces? So, forces acting in this direction is W sin theta. So, that will be coming as plus W sin theta, and then the force resisting or opposing the flow, that we can show by indicating that these are some external force. This external force can include the resistance due to side and surface, and if there is wind velocity, that can also be included, but of course in simple case we are not including those things, but any external resistance force that is opposing the flow can be included here. So, that is again in the opposite direction. So, we are writing minus Fe. So, external force or force acting on the system is this one on the system. So, these are the force on the system. Well, we may avoid this term also. The force on the system are like this, and then this should be equal to the change of momentum. So, our equation what we can write now is say q gamma by z, then B2 V2 minus B1 V1, that is the rate of change of momentum. This is equal to gamma Z1 bar A1 minus gamma Z2 bar A2 plus W sin theta minus Fe. This is our equation. So, this is basically a momentum equation, and that of course we can write in terms of rho also, but in this form also we can write. There is no difference between these things. And then if we make some simplification, if we just change some of the if we make some assumption, then some of the parameter can be neglected. Say for first assumption, say if we make the channel is horizontal, and because it is horizontal, so what will happen? This will lead to W sin theta become almost equal to 0. That means this term becomes 0 for this. And say if I consider it is frictionless, if I consider the channel is frictionless, so when I consider this as frictionless, then your Fe, suppose frictionless and air flowing is also of is not flowing with that speed, then say other resistance force fluid is ideal almost water. So, that all these other resistance force are 0. So, this can be neglected. Well, and then we can consider that within the section, again if we say that velocity variation within the section is negligible, velocity variation within the section is negligible. If we consider that, then what will happen? Our beta value, then our beta value will be equal to, where beta 1, beta 2, this is equal to 1. So, our equation get reduced to say Q2 V2 minus Q1 V1. Q2 V2 minus Q1 V1. That means again we can divide it by gamma, and then we can get it in this form, and this is equal to say G A1 Z1 bar minus G A2 Z2 bar. This can be now written as say, and V velocity and the velocity can be written as Q2 is there, this velocity can be written as Q2 by say A2, Q2 by A2, G is there, minus, so Q1, and this velocity can be written as say Q1 by A1 and G, and this is equal to A1 Z1 bar minus say A2 Z2 bar, and this can be further simplified or can be written as here say Q square by G A2 minus Q square by G A1 is equal to A1 Z1 bar minus A2 Z2 bar. Well, now here we can see in this expression, here we can see that This Q1 is there, and if it is continuity equation is satisfied, then Q2 and Q1 we can write as Q simply. Already we are writing that, so we need not put Q1, Q2, and this we can write like that. If we bring the two term in one side, one term in one side, then we can write that Q square by ZA1 plus A1 Z1 bar, taking this to other side and then bringing that to this side, we can write Q square by ZA2 plus A2 Z2 bar. These two terms are equal, and this term itself is called specific force. This term itself is called specific force. So, from the momentum equation, deriving the momentum equation, we can have that this specific force at this point and specific force at the second point are equal. Well, so here we have discussed in a very simple situation how we can derive continuity equation, how we can derive the momentum equation, but this is just a start, and we need to go into much more complex situation, and we need to understand how this continuity equation, momentum equation and energy equation can be derived for such complex situation. Well, thank you very much.